Welcome back to Science Click. Today, special relativity. Let's imagine a spaceship, as well as a planet, isolated in the depths of the universe. Suppose the spaceship is moving relative to the planet in a fixed direction and with a constant speed. One of the first fundamental properties of the universe is that in this situation, it is strictly impossible to determine whether it is the spaceship moving and the planet being motionless, or whether it is the spaceship being motionless while the planet is moving in the opposite direction. This is known as the principle of relativity. Whichever point of view we take, as long as the movement occurs in a straight line with a constant speed, it is equally valid to consider that it is the spaceship or the planet that is moving. Let's now imagine a passenger on the spaceship who decides to throw a ball forwards. For him, the ball is moving forwards with a certain speed. This speed corresponds simply to the impulsion which was given to the ball. But if we observe the same situation from the point of view of the planet, the ball seems to be moving faster, because its speed of impulsion combines with the speed of the spaceship itself. The strange thing is, if we now try to do this same experiment with light, using a torchlight for example, we see that whichever point of view is taken, the speed of light remains the same. Regardless of whether we look at it still or while moving, whether we shine it from a fixed point or one that moves, we will always see light as moving with one same exact speed. We say that this speed of light is invariant. The speed of light is a universal constant, fundamental, underlying the very structure of our universe. In our daily lives, the speed of light is way too high to enable us to see any effect of this principle. In only the blink of an eye, a light ray travels the distance between Paris and New York 6 times over. Nonetheless, this subtle property of light triggers drastic changes on the way we see the world. In special relativity, one fundamental idea is that two events can occur simultaneously for one person, but at different moments for someone else. To understand, let's imagine the following scenario. The passenger in the spaceship holds 2 torchlights, one which he points backwards and the other one forwards. His role will be to light the 2 torchlights exactly at the same time. He will then look at which moment the 2 light rays reach the edge of the spaceship. He begins by lighting the 2 torchlights at the same time. Since from his point of view, the spaceship stays motionless, the light rays will propagate both sides in the same way. Thus, they will reach the 2 ends of the spaceship at the same moment. For the passenger, the 2 events are simultaneous. Both light rays reach the 2 edges of the spaceship at the same moment. But let's now look at this same situation as it is perceived by an observer on the surface of the planet. We previously saw that the speed of light was a constant. Therefore, when the 2 torchlights are turned on, light will spread with the same speed on both sides. But at the same time, the spaceship is moving forwards. As such, the light ray sent towards the left will reach the back of the spaceship before the light ray on the right reaches the front. From this point of view, the 2 events are not simultaneous. The light rays do not reach the 2 sides of the spaceship at the same time. To explain this paradox, we must put to the side our intuitive understanding of time. In the previous situation, if the light ray on the left reaches the edge of the ship before the light ray on the right, this is in reality because the rear of the spaceship is slightly in the future compared to the front of the ship, which is slightly in the past. When it is noon in the middle of the spaceship, it might already be 1 PM at the back of the ship, while it is only 11 AM at the front of the ship. From the perspective of the passenger inside the ship, the clocks are perfectly synchronized. For him, it is noon in all parts of the ship. It is the act of observing from a moving point which desynchronizes the back and the front of the ship, one from the other. More generally, when an object moves with a very high speed compared to us, we observe that the front of the object lags in time with respect to the rear. If we placed, for example, two people of the same age, we would observe from the planet that the person at the front of the ship is slightly younger, while the one at the back would be slightly older. One direct consequence of this phenomenon is what we call length contraction. As we previously saw, when it is observed from the planet, the rear of the spaceship is slightly in the future. But since the spaceship is travelling in time, if the rear of the ship is in the future, it is also slightly ahead compared to its movement. Equally, the front is slightly behind compared to the movement of the spaceship. The global length of the ship therefore sees itself contracted in the direction of its speed. At ordinary speeds, this contraction is minimal, almost undetectable. For example, a car moving at full speed on a highway will only be contracted around the length of an atom nucleus. But the closer we get to the speed of light, the more this contraction phenomenon becomes important. If our spaceship could travel at 85% the speed of light, its length would be contracted by half. And at 99.5% the speed of light, its observed length would only be a tenth of its original length. In this situation, seen from the planet, the spaceship would seem extremely contracted. But from the point of view of the passenger who is inside, it is not the spaceship that is contracted, but the planet, as from his point of view, it is the planet which is moving and not the spaceship. Finally, a third direct consequence of the invariance of the speed of light is what we call time dilation. To understand this, let's consider the following experiment. The passenger inside the spaceship will grab a flashlight once again, this time pointing it towards the ceiling. At a given moment, he will turn on the light and observe the time it takes for the light ray to reach the ceiling of the spaceship. Once again, the problem changes if we decide to observe the same situation, but from the planet. For the observer on the planet, the spaceship and the passenger inside are both moving. Thus, the beam of light will have to travel not only the height of the ceiling, but will also have to travel towards the right, following the movement of the spaceship. From this point of view, the light ray must travel a greater distance. Consequently, just as it takes more time to cross a road diagonally rather than by its width, it will take light longer to reach the ceiling of the spaceship. For this observer, watching the situation from the planet, the light ray has thus taken more time to reach the top of the spaceship. In general, this observer will see the insides of the spaceship evolving in slow motion. If the passenger on the ship decided to show him a clock, from the planet we would see this clock tick in slow motion. More generally, when an object moves extremely fast compared to us, we see its rear and front desynchronized, its length contracted, and its evolution in slow motion. To sum up these phenomena, let's focus on the precise case of muons. Cosmic particles frequently penetrate into the high atmosphere. These cosmic particles filled with energy will progressively disintegrate until they form elementary particles, which we call muons. In a normal situation, these muons have an extremely short lifespan. They disappear after only a few microseconds. However, when we try to detect them from the surface of the Earth, we see that a great number of these muons still manage to reach the ground. This paradoxical situation can be explained thanks to the phenomena which we previously saw. Since the muons falling towards the ground can reach extremely high speeds, close to 99.5% the speed of light, we need to consider length contraction as well as time dilation. On the one hand, let's begin by placing ourselves from the point of view of a muon. For the muon, it is the Earth, and in particular the atmosphere, which are moving very quickly in its direction. Due to length contraction, the muon will thus see a contracted atmosphere, which is much thinner, and which it will therefore have time to cross entirely before disappearing. On the other hand, if we place ourselves from the point of view of an observer on Earth, it is the muons which are moving with a very high speed. Due to time dilation, we will see the muons as evolving in slow motion, and as such, their lifespan will seem greater to us. Once again, muons will have the time to reach the ground well before they disintegrate. To conclude, the simple fact that the speed of light is constant triggers some major consequences on the way we see the world. When an object is moving compared to us, in a straight line and with a very high speed, we see it evolving in slow motion, while it also seems contracted in the direction of the movement. This understanding of the relativity of time and space, depending on the movement of objects, is what we call special relativity. It teaches us that time and space are not absolute, that two observers can potentially perceive them differently. It also triggers a great number of effects, such as the fact that it is absolutely impossible to go beyond the speed of light, since to only reach this speed would require an infinite amount of energy. However, this type of relativity is labelled as special because it only applies in very simple cases, mostly for movements that occur in a straight line with a constant speed. Length contraction and time dilation are not adequate to describe other types of movement, for example changes in direction, accelerations, slowdowns, or even rotations. To do this, it will be necessary to adopt a much more thorough theory, which enables us to account for gravitational pull on the basis of a distorted geometry of space and time. This is the theory of general relativity.